All right, number 5 and number 6 and number 7 all concern themselves with power, right? So number 5 says rank the energy dissipated by each resistor over a certain amount of time, and that energy consumption per time, well, of course, that is power, right? So let's discuss what's going on here. So we have a certain amount of total current that leaves the battery, and it comes to this point where some of it splits down this branch, and the rest of it goes down this branch, and of course these two are in parallel with one another. So how can we tell how much current is going down each branch, and why do we want to know that? Well, we're trying to rank the power, and one power formula is IV. And what do we know about each branch is that they both have a common voltage. And so if I can find out like at least the ratio or the percentage or a portion of the current going down each branch, I can start comparing the power between one branch and the other. So taking a look at this branch here, I can see that its effective resistance down that one wire is 400 ohms. All right, I took the 300 and the 100 and I added them together. So this one wire has an effective resistance of 400 ohms compared to the 200 of the other wire. So what we can do then is say that since this 200 is 1/3 of the resistance between these two, it's going to get 2/3 of the current, which means this is going to get 1/3 of the current down this branch here. Now, in terms of power, then, since they have the same voltage, let's take a look at the power. And since they have the same voltage, that's going to be the same for both of them. Well, then the branch that has the 200 ohm resistor in it will have 2/3 IV compared to this one, which would be 1/3 IV. But let's take a look at those individual power dissipations from the 100 and 300 ohm resistors. And also we could use the I squared R, and I think that's probably going to be the better approach here. You'll see why in a second. So if we just do I squared R for this branch, we have the I of 2/3 I. We're going to square that and times it by the R value of 200. So I have 2/3 I squared times 200. And so this is going to come out to be about 89 I squared. All right, now let's compare that to the 100 ohm resistor. And I'm just going to use the I squared R. And I know that the value of I going through that 100 ohm resistor is going to be 1/3 I. And of course, we need to square that and multiply that by the resistor's value of 100. And this comes out to be about 11 I squared. All right, so now we can compare these two. And lastly, we just need to now compare, I'll do it over here, the power in the 300 ohm resistor. And we can see that it's just going to be 3 times what this value is. So it's going to be about 33 I squared. So now I have my power in some comparable unit of I square, and I square. And so we have ourselves the power of the 200 is greater than the power of the 300, which is greater than the power of the 100. Number 6 is just like number 5, except that it has this extra bulb there, right? So if we take a look at these here, it's the same as what's going on this. However, the only difference is instead of having different value of resistors, we have they're all the same value. So let's see how that works out. Once again, we have a total current that is going to be going through this guy with its resistance. And we could have a power then it would be I squared, I total squared times its resistance of R, right? And let's see how it compares to this branch and this branch. And so this bulb here, right, just like for the same reasons that was in the other problem above this, right, we have R versus 2R, just like we had 200 versus 400, right? So this is This is 1/3 of the total resistance of these three, and so it's going to get 2/3 of the current going through it. And likewise, this branch is going to get 1/3 of the current that goes through it, right? So the current comes into this junction here, and 1/3 of it goes through those two bulbs, and 2/3 of it goes through this one bulb, right? So go see that power now is 2/3 I squared R for this one, and this will now be 1/3 I square that times that R value, and this will also have that same one. So these two are going to be the same power value, and now we could put them into some ranking. And so we have that this bulb number 1, is greater than bulb number 4, which is greater than both bulb number 2 and 3, which are equal to one another. And so 1, 4, 3, and 2. Lastly, number 7 is the same setup, and it's talking about power being dissipated, and it wants to know about this guy here. How can we make the power dissipated through that resistor increase? Well, if that resistor value is not going to change, and the only other two things that can be manipulated are the voltage and current, I guess the answer would be like, which of those two answers will allow either A, the voltage to be increased across this parallel branch and thus this one resistor, or B, what would allow there to be more current going through this branch. If either the I or the V are increased, we can increase the power dissipated by that resistor. So 2 of those 4 answers on 7 should make that possible.